Have you ever wondered why anything exists at all? Why there is something rather than nothing? Today, we embark on an extraordinary journey to uncover one of the deepest mysteries in physics and cosmology, the enigma of antimatter and its role in the very existence of our universe. If you're fascinated by the forces that shaped reality, give this a like. Share it with a curious friend, and let's travel together through the veil of time, space, and the most elusive elements of our cosmic makeup. In the earliest flickers of time, the universe was not the grand expanse of stars, galaxies, and worlds we now see through the eyes of telescopes. It was an almost inconceivable chaos of unimaginable heat and density, a singularity erupting into expansion, seeding everything that would one day become reality. From this explosion of being, known as the Big Bang, the universe began its flight, from nothingness into form. But there, at the very beginning, a question emerges that has haunted scientists for generations. Why does matter dominate the universe, when its mirror image, antimatter, should have existed in equal measure? To understand this conundrum, one must first grasp the nature of antimatter. For every type of particle known to modern physics, there exists an opposite, an antiparticle. Where the electron carries a negative charge, the positron bears a positive. And where protons radiate positivity, antiprotons shimmer with negative force. These counterparts are not merely theoretical, they are real. And when they meet their opposing particle, a phenomenon of annihilation occurs, releasing pure energy in a brilliant flash of photons. It is this annihilation, this elegant self-destruction, that renders the puzzle all the more baffling. If, as our models predict, the Big Bang produced matter and antimatter in equal quantities, they should have annihilated each other entirely, leaving behind only a glowing sea of photons. And yet, here we are, worlds made of matter, stars that blaze with atomic fuel, sentient beings who ask why. The silence of antimatter in the cosmos is not from lack of trying to listen. For decades, scientists have searched the skies and the subatomic world for signs that antimatter still lingers in significant quantities. Satellites equipped with particle detectors soar above Earth, capturing high-energy rays and cosmic particles in hopes of glimpsing an antinucleus or antiparticle that defies current understanding. Deep underground, massive detectors wait in stillness, their chambers chilled and shielded from interference, poised to catch fleeting flashes of annihilation. The results, though mesmerizing, yield a somber truth. Antimatter is extraordinarily rare. So rare, in fact, that every star, every galaxy, every observable corner of our known universe is composed almost entirely of matter. But why? The standard model of particle physics, our most trusted blueprint for the fundamental forces in particles, provides a framework for how particles behave, yet even it fails to account for the imbalance. According to this model, every reaction that creates a particle should create its antiparticle twin. This symmetry, known as CPT symmetry, charge, parity, and time, holds the universe to a certain fairness. But the cosmos we observe is not fair. It is asymmetrical. It favors matter. Somewhere in the early seconds of existence, this symmetry must have broken. And so we look to those ephemeral instants after the Big Bang, less than a second old, the universe a roiling broth of energy transforming into particles and antiparticles. In this epoch of formation, processes were occurring at energies we can scarcely reproduce even in the most advanced particle colliders. Theories emerge like whispers from the void. Could there have been a slight bias, a preference in the way certain reactions unfolded? Might there exist a mechanism, subtle and rare, that tilted the scales just enough to let matter survive? This leads us into the realm of baryogenesis, the theoretical process by which the asymmetry between baryons, protons and neutrons, and antibaryons emerged. For such an imbalance to arise, three conditions must be met, known as Sakharov conditions, after the Soviet physicist Andrei Sakharov, who articulated them in 1967. First, baryon number violation. Some reactions must be able to change the total number of baryons. Second, C and CP violation. The laws of physics must treat particles and antiparticles differently, especially under charge and parity transformations. Third, a departure from thermal equilibrium. The universe must have cooled in such a way that these reactions couldn't reverse themselves perfectly. CP violation has been observed. In rare decays of certain mesons, short-lived particles composed of a quark and an antiquark, experiments have detected minute differences in the behavior of particles versus antiparticles. But the effect is minuscule, far too weak to explain the vast matter dominance we see today. If CP violation is the answer, it must be lurking in processes we've yet to uncover or in particles beyond the standard model. The hunt for these unknowns becomes the quest of modern physics. Supersymmetry, a theoretical framework proposing that every particle has a heavier superpartner, could offer the tools needed to explain the imbalance. In this extended landscape of particles, new pathways for CP violation might exist. New forces that operated only in the earliest moments, now long vanished from direct detection. Though supersymmetry has not yet been confirmed by the Large Hadron Collider or other experiments, it remains a tantalizing hope. Meanwhile, cosmologists turn to inflation, a theory that the universe underwent a period of rapid expansion moments after the Big Bang. If inflation occurred with certain properties, it could have created pockets of space with differing baryon asymmetries. Our observable universe could be just one such region, chosen by the luck of cosmic lottery, where matter gained the upper hand. Some speculate that entire regions of the cosmos may be antimatter dominated, separated from us by voids or hidden beyond the reach of light and time. But this idea raises its own difficulties. Wherever matter and antimatter meet, they annihilate in bursts of gamma radiation. If massive antimatter galaxies existed, we would likely detect this gamma-ray signature at the boundaries between domains. Yet the sky remains silent. The mystery deepens when we examine the subtle interplay of quantum fields. Every particle exists not only as a point of matter, but as a ripple in an underlying field, like a note played on a vast, invisible instrument. The Higgs field, discovered through its particle manifestation in 2012, gives particles mass. Could other unknown fields have influenced the particle-antiparticle ratio? Could the universe itself possess a memory, a quantum fingerprint, of the conditions that led to the imbalance? In the heart of this mystery lies a poetic tension. The very fact of our existence, the ability to question, to think, to create, hinges on a fundamental asymmetry in nature. Were the balance perfect, the universe would be a sterile bath of photons, no atoms, no stars, no minds. A universe without difference would be a universe without story. Matter won, barely, perhaps by 1 part in a billion. And that sliver of triumph, that narrow margin, is the reason you are here. Some researchers look not to the vastness of space, but to the fleeting world of neutrinos, ghost-like particles that rarely interact with matter. Neutrinos may hold secrets of their own, perhaps even violating CP symmetry in ways more pronounced than other particles. New experiments aim to detect such behavior, peering into the mechanics of these wraith-like entities, hoping to catch a glimpse of cosmic preference coded into the subatomic ether. Still others push the boundaries further, venturing into multiverse theories, where our universe is but one of countless realities, each with its own laws and balances. In some, perhaps antimatter prevailed. In others, no asymmetry arose and nothing remained. Ours is special not because we are at the center, but because it is one where existence could flourish. Life arises not from inevitability, but from exquisite probability. The story of antimatter is not a tale of absence, but of silent survival. It is not that antimatter never existed. It did in abundance. It danced in creation's fire alongside matter. But something happened, an unknown tilt, a mysterious skew that allowed matter to remain. That slight imbalance birthed galaxies, forged the periodic table, lit the stars, and opened the doorway for sentient thought. And so we continue to ask, not only why the universe exists, but why it exists the way it does. What breath, what law, what mechanism whispered favor onto matter? What cosmic decision, whether born of chaos or law, rendered the stage upon which we now ponder these mysteries? In the lingering heat of the young universe, less than a second old, the particles that would one day compose all matter still surged and scattered in a dense plasma of searing energy. Time, as we understand it, had barely begun its silent march forward. But even in that chaotic birth cry, a pattern was forming, one that would come to define everything we know. The dance of particles and antiparticles had started, and with each encounter came both annihilation and the whisper of survival. The universe cooled rapidly, an expansion not of matter alone but of space-time itself stretching. As energy densities dropped, particles began to freeze out, no longer able to spontaneously arise from the raw energy around them. Protons and neutrons emerged and in their wake trailed the shadows of what did not remain. The antimatter that should have matched them vanished in mutual destruction. But matter persisted. Somehow, a small excess of matter particles managed to avoid their fated encounter with their antiparticles. It is estimated that for every billion pairs of matter and antimatter particles, there was one extra particle of matter. That solitary survivor, multiplied across the vastness of space-time, became the foundation of all existence. It is in this small number, this infinitesimal margin, that the entire structure of the cosmos stands. All stars, all planets, every atom in your body, each breath and heartbeat and thought, all owe their presence to that microscopic imbalance. The scale of this accident, if it is an accident, is staggering. A 1 in a billion chance gave rise to everything. But chance may not be the full story. As the search for the origins of this asymmetry continues, physicists are compelled to ask, was this imbalance written into the very laws of nature? In labs across the world, from the Large Hadron Collider beneath the soil of Switzerland and France, to the Super Kamiokande detector buried deep under Japan's mountains, humanity reaches into the smallest structures of the universe to find a clue. With powerful magnets and high-energy collisions, we recreate the conditions of the early universe in tiny flashes of recreated genesis. We search for asymmetry and decay patterns, for particles that should not behave differently than their mirror selves, and yet somehow do. The idea of symmetry is more than aesthetic. It is fundamental to physics. Nature has long been understood to value balance. Conservation laws of energy, momentum, charge are symmetries made concrete. But as we probe deeper, we find that some symmetries are violated. Charge conjugation symmetry C, which asserts that physics should remain unchanged. If particles are swapped for antiparticles, does not always hold. Nor does parity symmetry, P, which involves the reflection of spatial coordinates. In certain weak nuclear interactions, particles show a clear preference for one direction over its mirror. Combined, C and P violations suggest that the universe has an intrinsic handedness, a bias. It is in this break from perfection that matter found its escape, and yet these violations we observe are not sufficient to explain the cosmic imbalance. They are subtle, whispering irregularities in otherwise balanced laws. For matter to emerge dominant, a grander violation must have occurred, one more potent, more primordial. And here is where theory outpaces experiment, and the mind must race ahead of observation. The possibility arises that there was a time before time, an epoch where the fundamental forces we now separate, electromagnetic, weak nuclear, strong nuclear, were united. In such a state, governed by grand unified theories, the very concept of particle and antiparticle may have differed. Perhaps in that unified field, baryon number was not conserved, and interactions allowed matter to emerge in surplus. If true, then our universe bears the fingerprint of a deeper, more elegant unity, now fractured into the forces we know. But proof of such theories remains elusive. Our tools, however mighty, cannot yet reach into the Planck epoch, the first 1043 seconds of existence, where quantum gravity ruled, and where the very fabric of space-time fluctuated like a stormy sea. It is in this inaccessible moment that many believe the asymmetry began. The inflationary epoch that followed could have frozen this imbalance into the structure of the cosmos, spreading it far and wide. In this framework, the asymmetry is not a fluke, but a result of quantum fields and symmetry-breaking events that shape the very identity of our universe. The Higgs field, which endows particles with mass, is one such field that underwent a phase transition as the universe cooled. There may be others, fields we have not yet observed, whose dynamics favored matter in subtle, powerful ways. These hypothetical fields, sometimes called baryogenesis fields or scalar fields, could hold the key to understanding why we exist. Meanwhile, the story of antimatter continues not only in the cosmos, but in technology and medicine. In laboratories, antimatter is created routinely, though in minute quantities. Positrons are used in PET scans, helping doctors peer inside the living body with exquisite precision. In accelerators, antiprotons are corralled and studied, their properties compared with protons in a quest for differences that might illuminate the origins of asymmetry. Even the International Space Station houses detectors that scan the heavens for antimatter nuclei, hoping to glimpse relics of a time when matter and antimatter battled for dominance. But our search is not limited to detection. Theoretical physicists model scenarios with exotic particles, heavy neutrinos, leptoquarks, axions, that might mediate the transformation of energy into a lopsided mixture of matter and antimatter. In one model, known as leptogenesis, the asymmetry begins not with baryons but with leptons, lightweight particles such as electrons and neutrinos. Heavy, unstable right-handed neutrinos, if they existed in the early universe, could decay in a way that favored matter, creating a lepton asymmetry that later transformed into a baryon asymmetry through high-energy processes. The elegance of leptogenesis lies in its connection to known phenomena. The tiny masses of neutrinos, confirmed through the observation of neutrino oscillations, suggest that new physics may be lurking nearby. If we can understand why neutrinos are so light, we may uncover the same physics responsible for matter's dominance. And if we detect CP violation in neutrinos, differences in how they and their antiparticles behave, we may come one step closer to solving the mystery of our own existence. There is a poetic irony in this chase. We search for the reason we exist by studying the thing we cannot find, antimatter. The more we look for it, the more its absence speaks volumes. The silence of antimatter is the sound of a cosmic preference, a choice carved into the laws of nature. And it is this silence that gives voice to the atoms, molecules and structures that make up life. In reflecting on antimatter, we reflect on symmetry and its breaking, on balance and the necessity of imbalance. The universe, it seems, requires imperfection. Perfect symmetry is sterile. It is in the flaw, the skew, the subtle nudge away from equilibrium that creation takes root. Life itself is asymmetrical. DNA coils in one direction. Amino acids favor one chirality. Even our brains are asymmetrical, with specialized regions for language, vision, emotion. As in physics, so in biology, difference gives rise to identity. So we continue to build our detectors and design our theories, not merely to find antimatter, but to understand what its absence tells us about the nature of reality. The answers may reside in dark matter, another invisible player in the cosmic drama, or in dimensions curled up beyond our perception. They may be written in the code of string theory, or etched in the fluctuations of quantum foam. Wherever they lie, they call to us through the void. A summons to keep asking. Our ancestors once looked up at the stars and wondered why the heavens burned. We now know the stars are nuclear furnaces of hydrogen and helium, ignited by gravity and fusion. But beyond the fire, beyond the atoms themselves, lies the question they could not ask. Why is there anything to burn at all? Why, in the beginning, did matter not cancel itself into nothing? This is not merely a question of science, but of being. To ask why the universe exists is to ask why we are here to ask the question. It is to confront the deepest roots of existence, and to marvel that we can even pose the mystery. There is something inherently human in the pursuit of cosmic answers. To peer into the unknown and demand understanding is a defiance of silence, a refusal to accept that the universe simply is. As we consider the enigma of antimatter, we begin to unravel not just the mechanics of particles, but the philosophical implications of asymmetry. The quiet favoring of matter is not merely a physical detail, it is a cosmic signature that all we perceive was born from imbalance. In that primordial moment, when energy crystallized into form, the universe took a decisive path. A billion annihilations, followed by a solitary survival, repeated across the immense theater of creation, laid the foundation for everything. It is a story written not in language, but in particle interactions, symmetry violations, and quantum fluctuations. And yet, it is a story no less dramatic than myth, no less significant than the oldest tales of origin passed from generation to generation. To truly appreciate this, one must understand that antimatter is not evil matter, as once imagined in science fiction. It is not shadow or darkness, it is a mirror, a perfect twin in every measurable way except in charge and spin. When Carl Anderson first observed the positron in 1932, a particle identical to the electron but bearing a positive charge, he confirmed that nature embraced this duality. For every building block of matter, there existed an equal and opposite component. The universe is not just matter, it is matter and the potential of its negation, bound together in a dance that gave rise to light. In controlled environments, antimatter can be trapped, studied, and compared. In the vacuum chambers of CERN's antiproton decelerator, physicists have created antihydrogen, an antiproton orbited by a positron. These antiatoms are tested for anomalies, as researchers look for the smallest cracks in the cosmic mirror. Do they fall at the same rate as regular matter under gravity? Do they absorb and emit light in identical patterns? Every answer found thus far affirms the mirror. But perfection in the small makes the mystery in the large even more pronounced. Why, if antimatter is so identical, so symmetrical, has it all but disappeared? The absence of antimatter challenges our understanding of initial conditions. Could it be that the Big Bang itself was asymmetrical? Or is the universe not symmetric in a fundamental way after all? We often assume symmetry as a kind of sacred truth, a divine balance encoded in the fabric of reality. But nature does not always favor symmetry. Sometimes it chooses function, emergence, and evolution over perfect form. Symmetry may be a phase, not a law, and if that is so, then perhaps the breaking of symmetry was not an accident, but a necessary step in the evolution of complexity. From the cooling of the early universe came the first nuclei, protons and neutrons bound together by the strong nuclear force. These particles, born from that tiny surplus of matter, formed the first building blocks of elements. In minutes, hydrogen and helium emerged. In stars, they fused to create carbon, oxygen, iron, the material of planets, of water, of blood and bone. But without that 1 in a billion imbalance, none of it would be possible. All would be photons, radiation endlessly washing over nothing. Even now, across the observable universe, we see this preference echoed. The light from distant galaxies travels billions of years to reach us, a cosmic fossil record of matter's endurance. Not once have we seen signs of large antimatter structures, not one anti-galaxy, no anti-stars or anti-worlds whose light would betray the presence of positrons and antiprotons. Instead, what we observe is uniform: matter, matter, and more matter. The silence of antimatter is not just local, it is universal. The question remains, if antimatter once was, where did it go? Did it simply annihilate in those first fractions of a second, its energy scattered into the cosmic microwave background? Or did it retreat into dimensions we cannot access? Some speculative theories propose that matter and antimatter were separated at birth, not annihilated, but divided. In brain cosmology, multiple universes or brains could exist side by side in higher dimensions. Our universe may be matter-dominated, while another, invisible to us, is antimatter-dominated. Gravity, which might leak between brains, could be the only sign of such a hidden twin. The notion is bold, but it captures something essential about human thought: the refusal to accept the incomprehensible as final. We invent models, test limits, and probe the invisible. We push the boundaries of colliders to energies that mimic the universe a trillionth of a second after its birth. And yet, every discovery only sharpens the edge of what we do not know. Among the most promising areas of current research lies in the continued study of neutrinos. These elusive particles are so small and so indifferent to normal matter that trillions pass through your body every second without interaction, and yet they hold clues that could unlock the matter-antimatter riddle. If neutrinos are their own antiparticles, a possibility known as the Majorana nature, they could provide a natural explanation for leptogenesis, where the asymmetry begins, with lepton violations that cascade into baryon asymmetry. If such behavior is confirmed, it would not only reshape particle physics, it would anchor our existence in the peculiar properties of the smallest and strangest particles in the universe. And what of time? The arrow of time, always moving forward, is tied deeply to the question of entropy and the evolution of the universe. But time, too, may have played a role in the disappearance of antimatter. If certain reactions violate time reversal symmetry, T, then we may discover that the cosmos has an inbuilt direction, not just in entropy, but in preference. Matter over antimatter. Existence over absence. There are those who believe we may never know the full answer, that the asymmetry is encoded in the initial conditions of the universe, unknowable because we cannot observe what came before. But that humility need not mean surrender. Each advance in theory, each experiment that narrows the possibilities, brings us closer to a truth that is both physical and existential. To understand antimatter is to understand the very logic of the cosmos. It is to ask whether reality prefers presence over negation, or whether existence itself is the consequence of an ancient and unrepeatable quantum coin toss. Some call this the fine-tuning of the universe, a set of physical constants and initial conditions so precisely aligned that life can emerge. The imbalance of matter and antimatter may be the greatest of these tunings, a tiny offset that permitted the rise of form, structure, and eventually, thought. If that is the case, then we are not simply the products of stardust, but of asymmetry. Our bones, our breath, our minds, they are the outcome of a fracture in perfection. And that fracture was not a flaw. It was the opening act of being. The beauty of this realization is profound. It reframes everything we take for granted. The fact that you are reading this, that your mind can entertain the vastness of the universe, that consciousness arose at all. None of this is guaranteed. It is all a consequence of an imbalance so subtle we have spent the better part of a century just trying to prove it happened. And still, the mystery deepens. Because with every answer, new questions unfold. If the imbalance was so slight, why was it not reversed later? Could there be undiscovered processes that preserve the matter advantage against the odds? Or could the universe itself be alive in a sense, not conscious, but dynamic, unfolding with purpose through its laws and limitations? In contemplating antimatter, we are not merely asking what is missing, but what remains. And what remains is everything. The stars in the sky, the ground beneath your feet, the breath in your lungs. All of it, a consequence of the universe's first great decision, to tip the scale, however slightly, in favor of matter, in favor of something over nothing. From the moment the universe favored matter, the unfolding of complexity became inevitable. That tiny asymmetry, insignificant in number, colossal in consequence, was the seed of all that would come. Atoms formed, stars ignited, galaxies spun into vast tapestries of light and gravity. Life, intelligence, awareness. These were not guaranteed, but they were made possible by that primal imbalance. As we stare into the depths of space and the equations of quantum mechanics, we begin to see a grand design, not in the sense of intentional creation, but in the emergence of intricate order from the most fundamental deviations in symmetry. This is the silent echo of antimatter, the absence that defines presence. Every photon released in an annihilation between matter and antimatter in the early universe contributed to the radiation that still fills the cosmos today, the cosmic microwave background, that faint afterglow whispering from every direction. It is a message not only from a time we can never visit, but from a process we barely understand. And yet, its uniformity and structure suggest that something profound occurred in those earliest instants, shaping the universe in ways that would ripple forward through time. But the mystery does not end with the particles we know. Beneath the surface of the standard model of particle physics, a remarkably successful yet incomplete framework, lies a deeper truth. The standard model does not predict the matter-antimatter asymmetry we observe. It includes CP violation, but not in sufficient magnitude. Thus, we know there must be more particles, more interactions, more layers to reality. Supersymmetry, a theory proposing a hidden twin for every known particle, offers one possible avenue. If these superpartners exist, they might have played a role in tipping the balance of the early universe. But despite decades of searching, they have not yet revealed themselves. Then there is the puzzle of dark matter, an invisible substance 5 times more prevalent than regular matter, yet completely undetectable through light. Could dark matter be the product of the same processes that created the matter-antimatter? Asymmetry? Some theorists believe so. In asymmetric dark matter models, the abundance of dark matter today is linked to the same asymmetry that left us with ordinary matter. If correct, then the question of why we exist is also the question of what the universe is made of. These threads weave together the known and the unknown, suggesting that the answers we seek lie not in isolation, but in the harmony of mysteries. In our search for those answers, we have also turned to the sky. The Alpha Magnetic Spectrometer. On the International Space Station scans the cosmos for high-energy particles that might hint at primordial antimatter. A single detection of antihelium would challenge everything we believe, because while antiparticles can be made in accelerators or cosmic ray collisions, entire antiatoms, especially heavier ones, would suggest the existence of macroscopic antimatter, structures, perhaps even anti-stars. So far, nothing definitive has been found. The silence continues, but it is not an empty silence. It is filled with the hum of possibility. Every null result shapes the landscape of theory, ruling out some pathways while illuminating others. In science, as in art, absence can be as powerful as presence. A blank canvas invites imagination. A missing symmetry invites inquiry. We do not yet know why antimatter vanished, or if it vanished at all, but in the pursuit of that knowledge, we deepen our understanding of what it means to be part of this cosmos. The implications stretch far beyond particle physics. They touch the origins of time, the birth of space, the fate of the universe. If matter emerged from an unstable vacuum, could it one day return to equilibrium? Might the universe decay into symmetry once more, annihilating all structure and form? The concept of vacuum metastability, the idea that our universe resides in a false vacuum, a temporary state, suggests that, under the right conditions, the entire cosmos could collapse into a lower energy configuration. Such an event would erase not only matter, but the very constants and forces we rely on. In a cruel inversion, the universe could one day restore perfect symmetry by destroying all that asymmetry allowed to flourish. This is not just theoretical morbidity. It is a reflection of how deeply tied existence is to imperfection. Our universe is stable enough to persist for billions of years, yet possibly unstable enough to fall apart in a cosmic heartbeat. That balance, on the edge of being and unbeing, defines our reality. And it began with the fate of antimatter. Philosophers once debated whether nothingness was more natural than something. The existence of anything at all, they argued, was a miracle, beyond comprehension. But modern physics has shown us that the vacuum is not empty, that nothingness is teeming with virtual particles, quantum fluctuations, latent fields. The real question, then, is not why there is something rather than nothing, but why this particular something survived. The answer, increasingly, seems to lie in the earliest moments of time, when the laws of physics themselves were forming, cooling, and choosing directions. One of the most haunting aspects of this mystery is that it may be singular. We may live in a universe where matter won only once, one universe, one moment of asymmetry. Or we may inhabit a multiverse where every possible configuration exists somewhere. In such a cosmic ensemble, there would be universes where antimatter prevailed, where nothing survived annihilation, where the constants were wrong for stars and life. In that view, we live not in the only universe, but in the one compatible with our existence. The anthropic principle suggests that we observe this asymmetry, because only such a universe allows observers like us to exist. But for many, this is unsatisfying. It replaces causation with selection. It offers a statistical inevitability rather than a mechanistic explanation. And so the search continues. We delve deeper into the properties of particles, hoping that somewhere, perhaps in the behavior of heavy mesons or the oscillations of neutrinos, we will find a pattern, an imprint of that first fateful preference for matter. And still, we wonder, what if antimatter has not disappeared, but is simply hidden? In vast regions beyond our observational horizon, could there exist domains of antimatter segregated by the vast distances of cosmic inflation? If such regions existed, the boundaries between matter and antimatter domains would produce immense amounts of radiation, gamma rays from annihilation events too powerful to ignore. Yet the sky is quiet. The radiation is smooth. The universe, as far as we can tell, is one-sided. In this quiet, we find meaning. The silence of antimatter tells a story no less profound than a discovery. It speaks of a universe that could have been nothing but chose through some process to be something. And in that choice lies every poem, every star, every breath drawn by every living thing. It is the most delicate triumph, a preference barely measurable, yet infinitely consequential. As we continue to push the limits of knowledge, from particle colliders to deep space observatories, we are not just chasing equations. We are seeking the origin of identity, of being, of why the cosmos sings instead of remaining mute. Antimatter, in its absence, is the clearest sign we have that the universe is not neutral. It is expressive. It is inclined toward creation, toward structure, toward life. And though we may never find a final answer, the journey itself transforms us. In asking why the universe exists, we become part of the answer. Our questions are fingerprints of the asymmetry that made us. Our curiosity, our wonder, our defiance of ignorance, they are all products of the same imbalance that once tipped the scales away from void and into form. To question the mystery of antimatter is to stand at the precipice of understanding and gaze into the abyss of the unknown. Each layer we peel back reveals another beneath it, as if the universe is not a puzzle to be solved, but a symphony to be experienced, each note echoing from an origin so delicate it escapes the grasp of even our most advanced instruments. Still, we listen, we measure, we imagine, and in that act the universe reflects itself through us. It is here, in this pursuit, that science and meaning intertwine. For every question about particles and symmetry and energy, there lies a deeper yearning, to know why anything exists at all. Matter, the substance of stars and skin and stone, is a mere residue of that ancient annihilation. That something survived at all is a miracle carved in mathematics. And that this something could evolve into beings capable of asking these questions, this is not just a triumph of biology, but of the entire cosmic narrative. The machinery of the cosmos, from the dance of quarks to the spin of galaxies, is powered by laws so consistent, so precise, that one might mistake them for inevitability. But nothing about this existence is guaranteed. The very laws themselves emerged from a period of spontaneous symmetry breaking, a phase transition in the early universe that selected one state among countless possibilities. Much like water freezing into ice, the cooling of the universe forced decisions to be made, structures to form, identities to emerge. In those fleeting microseconds after the Big Bang, the nature of reality crystallized, not randomly, but not deterministically either. There is agency in the laws of physics, not in a conscious sense, but in a structural sense, a capacity for choice encoded in the possibilities of the vacuum. At the heart of this capacity lies the concept of symmetry breaking. In the earliest moments, all forces were unified, indistinguishable. Gravity, electromagnetism, the strong and weak nuclear forces, all were part of a single, perfect symmetry. But perfection is unstable. As the universe expanded and cooled, this symmetry broke, and with it the forces split, diverged, differentiated. From this breaking came hierarchy. From hierarchy came structure, and from structure came life. But why did this breaking favor matter over antimatter? Why did it lean, however slightly, toward one form of existence? It is a question that has haunted physicists for decades. CP violation offers one clue, as it shows us that the laws of physics are not completely symmetrical between particles and antiparticles. In certain interactions, particularly those involving strange and beauty quarks, we observe a bias, a sliver of difference. But that sliver is not enough. The observed CP violation in the standard model is too feeble to explain the overwhelming dominance of matter. It is like trying to explain the light of a supernova with the flicker of a candle. So, we search for more. We test other sectors of physics, hoping to find interactions or fields that amplify this asymmetry. We consider leptogenesis, where the behavior of neutrinos may have set the stage for the matter imbalance. We explore the Higgs field, wondering if it contains not just mass, but memory, an imprint of the universe's earliest choices. Some even speculate that the universe was born in a quantum fluctuation, a probabilistic spark from a timeless sea of possibilities. In such a model, the preference for matter may be the result of a quantum roll of the dice, where our cosmos emerged in one particular configuration among a limitless multiverse of others. But here again, we must pause, because even if the preference for matter can be explained probabilistically, the improbability of our presence remains profound. The fact that the parameters of nature are tuned so delicately that the forces, the masses, the constants all fall within ranges that permit complexity, this still demands reckoning. The anthropic principle, which asserts that we must observe a universe compatible with our existence, offers an explanation, but not a resolution. It quiets the question without answering it. And yet, perhaps this is the beauty of the mystery. The fact that we can ask why at all is testament to the success of that initial imbalance. Without it, there would be no galaxies, no stars, no carbon, no questions. There would be only radiation, sterile and endless. But matter endured. The universe cooled and expanded. Hydrogen atoms formed. Gravity pulled them together, stars ignited, fusing elements in their hearts. Planets condensed. Chemistry danced. Biology bloomed. Intelligence awoke. Every civilization that has looked up at the night sky has done so from the same surplus of matter. From ancient astronomers tracking the paths of planets to modern physicists, smashing protons beneath the Earth, all of human inquiry rests on the quiet triumph of matter over antimatter. We are the descendants of that asymmetry, thinkers made of stardust, asking the stars why they shine. In this cosmic drama, antimatter is not the villain, it is the counterpoint, the other half of a universal tension that, once broken, gave rise to all we know. It may be gone or hidden or scattered beyond our reach, but its legacy is woven into every photon, every atom, every breath. It is the absence that defines the presence. It is the question that gives the answer its meaning. We often speak of progress in terms of knowledge gained, but there is a different kind of progress, the deepening of mystery. As our tools sharpen and our equations grow more precise, the boundary of the unknown does not recede. It becomes more defined. The more we understand, the more we realize what remains to be understood. The mystery of antimatter is not a puzzle, to be solved and forgotten. It is a threshold into deeper wonder. One day, perhaps, we will uncover the exact mechanism that tipped the scales. We may discover a new particle, observe a rare decay, or find that the vacuum itself is responsible. Or we may find that no single explanation suffices, that the origin of matter's dominance lies in the complex interplay of fields, forces, and chance. Whatever the outcome, the journey will have transformed us. For in pursuing the mystery of antimatter, we pursue the mystery of ourselves. Not just how we came to be, but why. Not just what we are made of, but what we are for. And in that pursuit, we become more than matter. We become meaning. So we build our detectors, we run our simulations, we listen for the faint signals that might whisper of antimatter's fate. We dream of colliders more powerful, of telescopes more sensitive, of equations more complete. And we tell the story. Again and again, we tell the story of how the universe once made a choice that led to light, to life, to us. There is a quiet defiance in existence, a rebellion against nothingness. This defiance is stitched into the very essence of matter, born in the furnace of the universe's beginning, carved into the structure of space-time itself. It is a defiance that echoes in every heartbeat, in the shimmer of every star, in the dance of galaxies across the cosmic void. It is the legacy of antimatter's absence and matter's improbable victory. We do not know why the balance tipped. We only know that it did, and because of that, we are here. The unfolding of that cosmic story begins not just with particles, but with potential, raw, undifferentiated, chaotic potential. In the earliest epoch, the universe was a seething quantum soup, a fog of energy where no boundary was yet drawn, no form defined. Time itself was embryonic, and space had not yet stretched into its grand expanse. Out of this primal haze emerged the laws, the frameworks of relation and transformation that would guide everything to come. These laws, etched not into stone, but into the invisible architecture of reality, dictated how energy could become matter, how symmetry could break, how structure could arise from formlessness. Among these laws were the conservation rules, energy, momentum, charge. But nestled, within them were the symmetries, those elegant truths that defined what could and could not happen. And among the most crucial was CP symmetry, the expectation that the universe would behave the same if particles were swapped for antiparticles and left and right were reversed. This symmetry, so beautiful in theory, is violated in practice. That violation is subtle, buried in rare interactions and fleeting particles, but it is real. And in that sliver of difference, the foundation of everything was laid. We have observed this CP violation in the decays of kaons and B-mesons, particles that flicker in and out of existence faster than thought. Their asymmetrical behavior in matter versus antimatter forms provides a tantalizing glimpse into the mechanism that may have favored matter in the early universe. But this glimpse is just that, a shadow on the wall. The full machinery behind the asymmetry remains hidden, perhaps behind energies we have yet to reach, or principles we have yet to imagine. The scale of this mystery is humbling. The dominance of matter we see today arises from a difference of just 1 part in a billion, roughly 1 extra particle of matter for every billion matter-antimatter pairs. That infinitesimal excess survived the Great Annihilation, the vast mutual destruction that followed the Big Bang. Everything else, the trillions of stars, the clouds of interstellar gas, the planets, the oceans, every living thing, is made of that remnant. We are the leftovers of a cosmic war, the fragile survivors of a primordial reckoning. That we exist is not a testament to might, but to margin. This realization forces us to look differently at the universe. No longer can we take its order, its structure, its complexity for granted. These are not default conditions. but hard-won victories. Each atom, each molecule, each thought is a celebration of improbability, and yet these improbabilities are our reality. They are our inheritance. In seeking to understand this inheritance, science becomes not just analysis, but reverence. We are not merely calculating decay rates and cross-sections. We are unearthing a sacred story, written in the language of fields and forces. And the further we probe, the more the story reveals its layers. Antimatter, once a theoretical ghost, became a tangible force. It can be created in the lab, stored, manipulated, but never have we seen it in bulk beyond our control. Never have we observed an antimatter planet, or even an antimatter asteroid. This absence is not silent. It is deafening. Experiments like the alpha magnetic spectrometer search the cosmos with open arms, hoping for a stray antinucleus, a signature too heavy to be explained by random particle collisions. Such a detection would rewrite the history of everything. It would suggest that antimatter, far from vanquished, persists in hidden strongholds, perhaps in isolated galaxies, mirror versions of our own. But the universe, so far, offers no such comfort. Its uniformity is a relentless whisper of a singular story. That matter won and antimatter vanished. Some have turned to the idea of baryogenesis, the theoretical process by which matter came to outnumber antimatter. Various models propose mechanisms involving exotic particles, phase transitions, or even interactions between different dimensions. In some scenarios, the early universe undergoes violent shifts, with scalar fields rolling through energy landscapes, igniting asymmetries as they go. These events may have occurred in the first trillionth of a second, leaving traces that now exist only in the distribution of galaxies or in the patterns of the cosmic microwave background. And yet, for all our progress, we are still searching. We build ever more powerful accelerators, like the Large Hadron Collider, and dream of its successors, reaching energies where new physics may emerge. We cool antimatter in magnetic traps, studying its properties with exquisite precision. We probe the differences between hydrogen and antihydrogen, searching for deviations that might crack the symmetry wide open. We chase shadows with light, hoping to glimpse the shape of the original imbalance. But what if the answer is not in what we find, but in how we see? What if the victory of matter over antimatter was not a moment, but a movement, a gradual unfolding of probabilities into certainty, an accumulation of tiny biases that cascaded into permanence? In this view, the universe becomes less a product of a singular cause, and more the outcome of cascading consequences, each step shaped by the last, each layer of complexity resting atop countless previous imperfections. And perhaps that is what existence truly is, the sum of all imbalances, an orchestra conducted by asymmetry, composed of mistakes that gave rise to meaning. Life itself is asymmetry, the left-handedness of amino acids, the twisted spirals of DNA, the directional flow of time. Even our thoughts have asymmetry, built from distinctions, contrasts, conflicts. Without difference, there is no pattern. Without imbalance, there is no movement. Without antimatter's absence, there would be no one to ask these questions. In that sense, antimatter did not lose. It fulfilled its role. It set the stage, drew the boundaries, created the conditions for what followed. Its annihilation was the price of creation. Its silence became the foundation of sound. The matter that remains is not the destroyer of antimatter, but its legacy, a form of continuation, not erasure. What was lost made way for what could be. So when we look at the stars, we are not seeing just distant suns. We are seeing consequences of laws chosen, of symmetries broken, of opposites resolved. Each glimmer is a reminder of what did not happen, of what could have been but wasn't. The beauty of the universe is not in its completeness, but in its partiality. It is in the nearly perfect, the almost symmetrical, the not quite balanced. In that almost lies everything we know, everything we are. When we seek the origin of the universe's matter, we are not merely tracing the evolution of particles. We are retracing the universe's first decision, the moment when symmetry surrendered to structure. In the void before form, possibility reigned supreme, and out of that quantum silence emerged a reality that leaned ever so slightly toward something rather than nothing. This lean is the signature of our existence. It is etched into every atom, every breath, every spark of thought, and yet its cause remains elusive, tucked behind veils we have not yet lifted. From the earliest epochs, matter and antimatter were born in equal abundance, for every electron a positron, for every proton an antiproton. The fabric of that primal firestorm shimmered with perfect opposition, a yin and yang in thermal harmony. But that harmony shattered. As the universe cooled, it did not simply condense, it decided. And in that decision, one side fell away. Matter endured. The annihilation that followed was nearly total. The early universe became a battlefield of mutual destruction. Particles and antiparticles collided in blinding flashes of gamma radiation. What should have been a mutual extinction became an act of selective survival. A tiny fraction, 1 part in a billion, was left untouched. That sliver of excess matter became everything. Stars, galaxies, planets, consciousness, a billion pairs, banished so that one might remain. That is the ratio on which everything rides. To understand this survival, physicists turn to the depths of quantum theory and the heights of cosmology. They look to interactions beyond the standard model, to violations of fundamental symmetries, to moments when the rules bent just enough to let imbalance take root. The CP violation observed in Chiron and B meson decays is real, but it is a whisper in a storm. It cannot account for the vast difference between what was and what remains. Something more profound must have occurred. In the theory of electroweak baryogenesis, the imbalance emerges from the transition of the universe from a high-energy symmetric state to a lower-energy broken one. During this transition, bubbles of the new phase may have expanded through space like steam forming in boiling water. At the boundaries of these bubbles, the laws of physics could have been skewed just enough to favor the creation of more matter than antimatter. These boundaries may have become arenas of creation, where the arrow of asymmetry pointed forward, carving the future out of thermal chaos. But this theory, like many others, relies on conditions we cannot yet reproduce, energies we cannot yet reach. We are left to piece together evidence from the periphery, from cosmic aftershocks and fleeting subatomic signals. We study the cosmic microwave background, the faint glow left over from the Big Bang, for clues. We build massive underground detectors shielded from noise and radiation to search for signs of proton decay or neutrinoless double beta decay, phenomena that could hint at physics beyond the known. We also turn to neutrinos, those ghostly particles that flood the universe in unimaginable numbers, yet rarely interact with anything. Neutrinos may hold the key. If they are Majorana particles, identical to their own antiparticles, it could imply that lepton number violation is real. And through a mechanism known as leptogenesis, such violations could translate into the matter-antimatter imbalance we observe. In this vision, the asymmetry is not a feature of all particles, but one birthed in the lepton sector, later converted into the baryon asymmetry we inhabit. Every theory that dares to explain the mystery of antimatter must answer 3 conditions, outlined by Andrei Sakharov in 1967: baryon number violation, CP violation, and departure from thermal equilibrium. These 3 pillars form the foundation of any viable path from perfect symmetry to the imperfect universe we now see. And yet, while the standard model offers hints, it does not satisfy them fully. We must look beyond, into supersymmetry, into grand unified theories, into the architecture of strings and brains. Supersymmetry, or SUSY, proposes that every known particle has a heavier superpartner. These superparticles, if real, could contribute additional sources of CP violation, and their decay in the early universe could drive the baryon asymmetry. They could also explain the mystery of dark matter, the unseen mass that binds galaxies together. But so far, despite the vast power of our colliders, no superpartner has been found. The silence is not defeat. It is a redirection, guiding us to ask new questions, build better instruments, and think more deeply. Theoretical physics stretches into even more speculative realms. Some models posit that our universe is but one of many, a multiverse in which different regions obey different physical laws. In such a scenario, our matter-dominated universe might be one bubble in a cosmic foam, selected not by necessity but by contingency. We exist here because this region permitted our kind of complexity. In other regions, matter and antimatter might coexist, or perhaps neither ever emerged at all. It is not an answer, but a framing, one that shifts the weight of mystery from law to landscape. Yet for all our efforts, we return again and again to the asymmetry itself. The survival of matter is the universe's original story. It is the event. Before all events, the act that shaped everything to come. Every structure, from atoms to galaxies, is a sculpture carved from that initial imbalance. And we, who ponder this mystery, are not outside it. We are of it. Our brains, our thoughts, our questions, all are made of matter. Our capacity to ask, why, is itself a result of the very thing we seek to understand. And perhaps that is the final paradox. To ask why matter won is to ask why we are here to ask at all. It is a question that turns inward, folding the fabric of inquiry into the object of inquiry. In this self-reflection, science touches something profound, something almost sacred. We do not seek answers only to know. We seek them to become more aware of what it means to be. Antimatter may be gone, but its story is not over. It lives in every equation, every experiment, every spark of imagination. It is the negative space that defines the image. It is the silence that makes the music possible. In the vast emptiness between galaxies, in the space between stars, in the shadows beneath the known, antimatter lingers, not as substance, but as memory. And so we continue. We theorize, we collide, we calculate, we search for violations, for particles, for echoes. We write papers, build detectors, question our assumptions. We wonder if somewhere, in some corner of the cosmos, the symmetry might still be perfect, the balance still preserved. We dream of finding an antimatter galaxy, not because we expect to, but because the possibility reminds us that the universe is bigger than our understanding. In this pursuit, we are more than observers. We are participants in a grand narrative, one whose meaning we are still writing. The mystery of antimatter is not a dead end. It is an invitation to look deeper, to reach farther, to listen more closely to the whispering void from which everything came. The whispering void from which everything came is not empty. It is filled with echoes, ancient and enduring. These echoes do not resound with sound or light, but with form, traces of matter, signatures of imbalance, the remnants of annihilation. They are not artifacts of destruction, but the very essence of survival. Every electron in your body, every proton in your bones, every atom that pulses with life is an echo of that ancient choice, to become, not to vanish. And so, to understand why the universe exists is not to understand matter alone, but to understand the absence of its mirror, the untold story of antimatter. Its fate is woven into every aspect of our cosmic history, from the smallest quarks to the largest galactic clusters. And in that story lies a greater question still. Was the universe always destined to become asymmetrical, or did it unfold from chaos into order by accident, like a coin spun through the infinite space of possibilities, landing on its edge for just a breath before tipping ever so slightly? In the silence after the Big Bang, the universe did not merely expand, it transformed. Cooling led to condensation. Symmetries began to shatter. In the early moments, the four fundamental forces we know, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were unified, indistinct. As the universe cooled, this unity fractured. First gravity broke away, then the strong force, and then the electro-weak force split, giving birth to electromagnetism and the weak interaction. It is during this electroweak epoch that many believe the imbalance between matter and antimatter may have been sealed. It's here that particle physics and cosmology entwine most tightly. The behavior of particles in this era was dictated by fields, cosmic blankets that pervade all space. One of these fields, the Higgs field, became central. When particles interacted with it, they acquired mass. The universe, once dominated by massless particles moving at light speed, now slowed, condensed, and gained structure. In this structured universe, imperfections mattered. Small differences in particle behavior, once smoothed by chaos, now led to divergence. One direction favored matter, the other favored oblivion. But why? The violation of symmetry, the tipping of balance, remains the most profound enigma. We have found instances where matter behaves slightly differently from antimatter, where a kaon decays more slowly, where a B meson reveals a preference. These are clues, not answers. They are brushstrokes on the edge of a vast mural, the shape of which we cannot yet see. And in this unseen pattern lies the reason we exist. Our search takes us not only to the smallest scales but also to the farthest reaches of space. We launch instruments like the Fermi Gamma Ray Space Telescope, hunting for signs of antimatter annihilation beyond Earth. We deploy the Alpha Magnetic Spectrometer aboard the International Space Station, scanning for heavy antinuclei that could suggest entire stars or even galaxies composed of antimatter. Each null result tightens the noose. Each silence tells us more about where antimatter isn't, shaping our understanding of where it might have gone. There are also experiments beneath the Earth, giant detectors buried deep to escape interference from cosmic rays. These sanctuaries of science watch for whispers of violation in the behavior of neutrinos, for signs that they may be their own antiparticles. If we find that the universe treats neutrinos differently than antineutrinos, if we uncover a subtle asymmetry in their oscillations or interactions, we might finally grasp the lever that tipped the cosmic scale. In the world of particle physics, time and direction matter deeply. A subtle asymmetry in the laws of physics means that processes running forward in time behave slightly differently than if reversed. This arrow of time is mirrored in our lives, in the aging of stars, the unfolding of galaxies, the pulse of life itself. And perhaps this arrow began with the matter-antimatter split. Perhaps the irreversible nature of time is a consequence of that first imbalance. This is not just physics, it is a philosophy of existence. To be here, to exist at all, is to be on one side of a fundamental divide. Every galaxy we see, every breath we take, is a marker of that divide. When we speak of antimatter, we are speaking of a lost reflection, a universe that could have been, one that mirrors ours not in light but in absence. It is the path not taken, the silence beneath the song. And yet, even in its apparent absence, antimatter plays a role. It challenges us to look deeper, to question the assumptions of symmetry, balance, and fairness in nature. The universe is not fair in the way we imagine. It does not distribute equally. It does not preserve all things. But in its partiality, it has created something extraordinary. Us. We might never find a cosmic pocket of antimatter. We might never detect an anti-helium nucleus drifting through intergalactic space. But that does not mean antimatter has no place. It had a role in shaping what we are. It defined the boundaries of survival. Without antimatter, there could be no matter. They were born together, and in their mutual destruction, they revealed a path forward. And perhaps that is the final irony. Antimatter in dying gave rise to life. It is the sacrifice written into the foundation of existence. Annihilation is not just an end, it is a transformation. What remains after the fire is what we build upon. The universe was born in fire, in fury, in a clash of opposites. But from that fury came form. From destruction, order. From imbalance, beauty. We live in a cosmos defined by this absence, not just the absence of antimatter, but the absence of certainty, the absence of completeness. Every answer we find opens new questions. Every discovery reveals more of what we do not know. And this is not a failure of science, it is its triumph. The pursuit of antimatter is a pursuit of understanding itself, a recognition that we are always on the edge of knowledge, looking into the unknown. This edge is where all meaning resides. It is where ideas become theories, where theories become experiments, and where experiments become revelations. We build machines that span kilometers. We cool particles to near absolute zero. We count events that occur once in a trillion years, all in search of the whisper of a vanished twin. That whisper continues to guide us. It is in the curvature of space, the drift of galaxies, the decay of particles. It is in the quiet silence of deep space and the roaring collisions inside particle accelerators. It is in the dreams of physicists and the awe of poets. It is a reminder that to exist is to be improbable, and to question is to be human. So we keep listening. We keep building. We keep imagining. The mystery of antimatter is not a riddle to be solved and forgotten. It is a compass pointing toward the deepest truths of our reality. It is the call of the cosmos, inviting us to understand why there is something, rather than nothing, why the universe exists, why we exist. To exist is to emerge from improbability and stand in defiance of perfect balance. The entire cosmic narrative, from the first glimmer of energy to the galaxies sprawling across the void, is founded upon a microscopic tilt, a bias in the law of being itself. That the universe exists at all suggests that symmetry, though elegant, is not absolute. It yields, it bends, and when it does, a world can be born from the smallest breach. The more we search the silence, the more we realize the precision of this imbalance. One extra particle of matter for every billion pairs of matter and antimatter. That's all it took. One part in a billion tipped the scale. And yet from that minuscule surplus, entire galaxies emerged. The stars are not made from abundance, but from remnants, ash from the fire, seeds from the annihilation. And as we study this ancient fire, we confront a question that is as unsettling as it is profound. What if the laws that created this imbalance are no longer in effect? What if the early universe contained properties and interactions that faded with time, leaving only their consequences behind? In that scenario, we are the fossils of a cosmic epoch that can no longer be recreated. The cause is gone, but the effect remains. This forces a new kind of scientific humility. Perhaps the origins of the matter-antimatter asymmetry lie in a regime of physics beyond our reach. Perhaps they occurred at energy scales far above those we can access, in domains of reality we can only infer. The Large Hadron Collider has pushed the boundaries of human engineering, smashing particles at nearly the speed of light, mimicking conditions close to the Big Bang. And yet, its discoveries may be only the faintest flickers of deeper truths. This is the challenge of fundamental physics. We are no longer simply looking outward. We are reaching downward, deeper into the very essence of what makes reality real. We are peeling away the layers of nature like an onion, each skin more subtle than the last. With every experiment, we approach the veil, knowing it may never fully lift, but that the act of reaching is itself a triumph. One possible path toward the origin of this asymmetry is through the unification of forces. In the first fractions of a second, the universe was governed by a single unified force, a grand symmetry that shattered as it cooled. Grand unified theories, or GUTS, attempt to reconstruct this primeval state, combining the strong, weak, and electromagnetic interactions into a single framework. These theories predict that protons may not be truly stable. Over unimaginable timescales, they may decay, leaving behind telltale particles. Detecting proton decay would not only transform our understanding of matter's durability, but also provide critical insight into the early mechanisms that allowed matter to survive over antimatter. Such decay would confirm that baryon number, a property previously thought to be strictly conserved, can be violated. And that violation is essential. Without it, the asymmetry we observe would be impossible. Experiments like Super Kamiokande in Japan and its successors are devoted to this quest. They wait in silence, watching vast tanks of ultra-pure water, waiting for the flash of a single proton's death. Years may pass without a signal, but each moment of patience is a wager on the universe's deepest secrets. It is the stillness of these detectors that listens to the loudest truths. Meanwhile, the neutrino, once thought massless and insignificant, continues to intrigue. These particles pass through Earth by the trillions every second, slipping through matter like ghosts. But when they do interact, their behavior hints at something extraordinary. They change identity. They oscillate between types, electron, muon, and tau, violating assumptions about fixed properties. These oscillations imply mass, and where there is mass, there may be asymmetry. If neutrinos are Majorana particles, indistinguishable from their own antiparticles, they could be the key to leptogenesis, a process where the decay of heavy, early universe neutrinos created more leptons than antileptons. That lepton asymmetry could then have been converted into a baryon asymmetry by sphalerons processes during the electroweak epoch. This is not just elegant theory, it is physics with consequences. The behavior of the universe, the formation of galaxies, the birth of stars, and the presence of life all depend on whether neutrinos obey the rules we expect or surprise us again. Future experiments like Dune and Hypercameo-Conde aim to pin down these behaviors with greater precision, to test the boundaries of our assumptions, and perhaps to reveal the hidden script behind the matter-dominated universe. But even as we refine our instruments and stretch our imagination, a deeper philosophical undercurrent rises. Is the universe's asymmetry necessary or accidental? Is there an underlying principle, a cosmic necessity, that demands this imbalance? Or are we living in a universe that just happens to have taken this path among many possible ones? The anthropic principle offers a provocative idea. Perhaps we live in a universe with a matter-antimatter imbalance because only such a universe can harbor observers like us. If antimatter had won, perhaps intelligent life made of antimatter would be asking the same question. If the balance were perfect, no atoms would exist at all. Only light, chaos, and silence. We see the universe not as it is, but as it must be for us to exist within it. Some find this line of thought dissatisfying, even circular. Others see in it a profound humility, that we are not the center of design, but the result of cosmic contingency, that what exists is not inevitable, but permitted. This perspective frames our existence not as a given, but as a marvel, a rare alignment of chance, law, and time. Still, science does not rest on philosophy alone. The quest to understand the fate of antimatter continues not just to explain the past, but to inform the future. The imbalance that defines our world might also help define what comes next. If we can harness the physics that governs these symmetries, we may discover new forms of energy, new states of matter, even new methods of communication or propulsion. The dream of antimatter propulsion, a staple of science fiction, is rooted in real physics. The energy released when matter and antimatter annihilate is unparalleled. 1 gram of antimatter could release as much energy as a nuclear bomb. Creating and storing antimatter is currently beyond our capabilities at any useful scale, but as our understanding deepens, who's to say what future technologies might emerge? Beyond practicalities lies something deeper still, a spiritual resonance. The story of matter and antimatter is a story of balance and imbalance, of creation through loss, of existence emerging from the narrowest thread of survival. It is a parable written in particles, yet echoing through poetry and myth. The serpent devouring its tail, the phoenix rising from ash, the light born of shadow. We are that light. We are the improbable survivors of a cosmic war that ended before time began. And in that survival lies a duty to understand, to honor, to remember, to seek the truth not only for knowledge's sake, but to comprehend the beauty of what it means to be. What does it mean to be a universe that remembers its origin through silence? In the absence of antimatter, there lies a kind of memory, not written in words or stone, but in the very fabric of space and time. Every fluctuation of a quantum field, every fold in the cosmic web, carries the faint signature of a beginning, shaped not only by expansion but by imbalance. This memory does not fade, it deepens. It is imprinted into the laws of nature, etched into the entropy that guides the arrow of time, whispered through the radiation that fills the darkness. We look back not only to uncover our history, but to understand our place within this extraordinary arrangement. Why did the early universe choose to favor matter? Or was it not a choice, but an inevitability triggered by mechanisms we have yet to fully comprehend? Could it be that hidden within the elegance of mathematics lies a subtle, profound imperative, one that tips the symmetry ever so slightly to allow something rather than nothing? We speak of the Big Bang as if it were an event, a single flash of light, but it was not a moment. It was a transformation, a change in state, a rupture in what came before. Before space, before time, before particles, there was only potential. And then, through processes we still struggle to articulate, that potential became form. In that form, matter and antimatter danced in perfect opposition, created in pairs, bound by symmetry. And in their dance, they annihilated. But not completely. What remained, the slight excess, the whisper of imperfection, became the canvas of everything. And we must ask, what introduced that imperfection? Could it have been fluctuations in the vacuum, minute and spontaneous? Could it have been a field unknown to us still that existed briefly and tipped the balance through an asymmetric decay? Or perhaps it was a phase transition, like water freezing into ice that crystallized asymmetry out of what was once uniform. The theory of cosmic inflation offers a stunning picture of this. It suggests that in the earliest fraction of a second, the universe expanded exponentially faster than the speed of light. This inflation smoothed the cosmos, stretched quantum fluctuations into galactic seeds, and may have created conditions ripe for symmetry breaking. Within that explosion of space, a mechanism may have emerged that nudged the scales of balance, an infinitesimal favoring of matter over antimatter. And yet, despite all these ideas, there is still no consensus. The standard model of particle physics, as powerful as it is, cannot fully account for the magnitude of the asymmetry. It provides the tools, the framework, the language, but not the story. Something is missing, and that missing piece calls out to us not as an absence but as an invitation to expand our knowledge, to break the boundaries of the known and step into the vastness of the possible. Perhaps the answer lies in supersymmetry, the idea that every known particle has a heavier twin. If true, supersymmetry could open the door to new interactions, new decay pathways, new chances for imbalance to emerge. It could bridge the gap between matter and antimatter, revealing why one survived. Or maybe the answer lies in extra dimensions, curled up in scales beyond our perception. The universe may be more complex than our three-dimensional intuition allows. In such a reality, forces and fields could behave differently, and symmetries could be broken not in our observable space but in realms hidden just beyond reach. These ideas, once considered speculative, are now active areas of research, tested not only through theory, but through particle collisions, cosmic observations, and the steady refinement of our instruments. And through it all, the antimatter mystery remains. It is not a roadblock, but a beacon. It pulls us forward. It reminds us that nature does not owe us easy answers. It offers hints, glimpses, the occasional paradox, and demands that we rise to meet them with imagination and rigor. In searching for antimatter's fate, we are searching not only for particles, but for meaning. For the origin of this asymmetry is not a detail, it is the defining feature of our universe. It is the reason there are stars, planets, chemistry, biology, thought. Without that imbalance, the universe would be sterile, a burst of light swallowed by its own perfection. Symmetry would have erased the canvas before the first stroke could be painted. Instead, imperfection gave rise to beauty. Incompleteness, gave rise to story. This understanding changes how we see the world. It reveals that the most fundamental truths may emerge not from stability, but from fracture. That to be is to be the result of a broken balance, a balance broken just enough to allow complexity, variety, and change. We are born not of harmony, but of tension. And in that tension, possibility flourishes. As we peered deeper into the cosmos, we also peered deeper into ourselves. The atoms that compose our bodies were forged in stars, stars that collapsed and exploded in supernovae. But those atoms are only possible because matter survived. The same imbalance that allowed galaxies to form also allowed hearts to beat. Our biology is an echo of cosmology. And as we gaze outward, the universe becomes a mirror. We begin to realize that the distinction between the observer and the observed is less than we thought. We are not separate from the cosmos. We are an expression of it. Every experiment we conduct, every theory we build, every mystery we unravel is the universe, studying itself, trying to remember what it once was. Perhaps this is why the antimatter puzzle haunts us. It is not just a physical problem. It is a memory half lost. It is the universe looking into its past and finding a question it cannot answer alone. It needs us, our minds, our tools, our curiosity. The act of asking is itself part of the solution. The mystery of antimatter is a collaboration between existence and consciousness. And so we build, we question, we wonder, we refine our models, challenge our theories, and expand the frontier. The search for antimatter's legacy is a bridge between physics and philosophy, between what is and what could have been. And walking that bridge is perhaps the most human thing we can do. We are creatures of asymmetry, born in a universe defined by a choice it never consciously made. And yet, from that unconscious choice emerged meaning. And in the search for that meaning, we find something greater than answers. We find purpose. We find the will to keep exploring, not because we must, but because we can. The universe is not obligated to make sense, but it often does, just enough to keep us reaching, dreaming, building. And in that reach, we become part of its story. A story written in particles and waves, in annihilation and survival, in questions and stars. To live in the aftermath of cosmic imbalance is to be suspended in a moment of rare fortune. We dwell in a universe where laws conspired, ever so delicately, to allow matter to triumph. And though the vanquishing of antimatter was silent, without violence it was absolute. There are no stars composed of antimatter in the distant galaxies, no islands of antihydrogen drifting through the cosmic web. Wherever we look, the fingerprint is the same. Protons, neutrons, electrons, matter, only matter. The antimatter that once matched it in perfect balance is gone, consumed in the earliest fires, leaving behind this subtle, persistent, exquisite residue. And yet perhaps gone is not quite right, for every process has a trace, and every trace, a story. In laboratories on Earth, we recreate those ancient processes. With enough energy, we produce antimatter, positrons, antiprotons, even antihydrogen. They exist only briefly, before meeting matter and vanishing in mutual erasure. But in that brief flash, we see what the universe once was. In the short-lived gleam of an antiproton, there is a memory older than stars, a remnant of the time when everything that is now possible was still uncertain. These glimpses remind us that antimatter is not fictional. It is not abstract. It is real, tangible, measurable. It obeys the same fundamental laws as matter, yet mirrors it with eerie precision. If not for the asymmetry, we could just as easily have been made of antimatter. If you replaced every particle in your body with its antimatter twin, if every proton became an antiproton, every electron a positron, you would be chemically identical. No one could tell, except the universe. And the universe would not be indifferent. Matter and antimatter annihilate upon contact, releasing pure energy. The scale of destruction from a mere milligram is staggering. In that collision, EOR MC2 is made manifest. And so, the separation of matter and antimatter is not just a structural quirk, it is a boundary between worlds. It is the reason stars can burn safely, the reason planets are stable, the reason we do not disintegrate in a flare of radiation. A universe where matter and antimatter mingled freely would be a universe without permanence. But what if, somewhere, somehow, antimatter has survived? Could there be regions of the cosmos where the initial imbalance was reversed, where antimatter dominates and matter was annihilated? This possibility is not ruled out entirely. Some theories allow for the formation of antimatter domains, vast and isolated regions cut off from the matter-dominated expanse. If these domains exist, their boundaries would be turbulent, radioactive frontiers where particles and antiparticles annihilate in ceaseless storms of gamma rays. Astronomers have scoured the sky for such signals, searching for the telltale glow of annihilation at cosmic borders. Thus far, none has been found. But the universe is vast, its scale dwarfs imagination. If antimatter galaxies exist, they may be far beyond the horizon of our observation. They may orbit different rules, anchored in their own asymmetric beginnings. In such places, life may have arisen in reverse, built from anti-atoms, walking across anti-soil beneath anti-stars. And if so, they too may wonder, why does matter exist? Why not antimatter? The very notion stretches the boundaries of thought, forcing us to recognize how narrow our perspective is. We live in one universe, with one history, governed by one narrative of imbalance. But could there be others? In the framework of the multiverse, each universe sprouts from quantum fluctuations, each with its own physical constants, its own symmetries or their absence. In one, matter may prevail. In another, antimatter. In others still, neither. The multiverse does not just expand space, it expands possibility. But even if we remain bound to this one universe, our curiosity transcends it. We ask not only what is, but what could have been. In this tension between reality and possibility lies the essence of scientific wonder. To understand antimatter's disappearance is to peer into the gap between laws and outcomes, between equations and events. It is to glimpse the engine that turns potential into existence. That engine may lie in processes we barely comprehend. CP violation, the phenomenon where the laws of physics differ slightly for particles and antiparticles, may hold the key. In the laboratory, we have measured CP violation in the behavior of certain mesons, particles made of a quark and an antiquark. These asymmetries are subtle, emerging only in the rarest decays, under the finest scrutiny. Yet they are real, measurable, undeniable. The laws are not perfectly symmetrical. The mirror, when held up to nature, cracks just enough to let something through. But the known sources of CP violation are too weak to explain the vast dominance of matter in the cosmos. Something stronger, something more ancient must have acted. New particles, new forces, unknown and undetected, may have orchestrated the early imbalance. And so particle physicists build ever more powerful colliders, searching for deviations, anomalies, patterns that whisper of deeper truths. The search is meticulous, slow, methodical, but within it is the thrill of discovery, the hope of finding the missing piece. It is not merely a scientific pursuit, it is an act of communion with the cosmos. Every equation written, every experiment conducted, every detector built is a declaration of faith in the intelligibility of the universe. That we can ask why the universe exists and expect a real answer is itself extraordinary. For billions of years, matter simply was. Only recently, with the emergence of conscious minds, did the universe begin to question itself. In us, the cosmos has gained the ability to reflect. This reflection is more than intellect. It is emotional. There is awe in the silence between galaxies, in the shadows cast by antimatter's absence. There is wonder in the knowledge that all we are comes from a forgotten imbalance. There is humility in the realization that had the coin landed the other way, there would be no coin, no toss, no observer, just equilibrium, sterile and eternal. But there is also purpose, not a cosmic purpose imposed from above, but a purpose we create in response. To know the universe, to trace its history, to tell its story, that is our purpose. The mystery of antimatter is part of that story. It is the opening chapter, the original drama. Without it, there would be no plot, no characters, no reader. We often seek meaning in the grand, in the vast, but meaning also hides in the minuscule, in the fractions and decimals, in the asymmetry of decay, in the anomaly of a particle's path. The universe did not shout its intention, it whispered. And in that whisper was a world. Our role, then, is to listen, to amplify the whisper into understanding, to transform the flickers of annihilation into narratives of origin, to honor the silence of antimatter not as a loss but as a gift, the gift of presence, of structure, of possibility. And if we never find the complete answer, if the origin of the imbalance remains forever just beyond reach, even then the search will have transformed us. It will have sharpened our minds, deepened our questions, connected us more intimately with the cosmos. In seeking to understand why antimatter vanished, we come to understand why we endure. We are not anomalies. We are inheritors. We are what remains when the fire cools, when the pairs vanish, when the dance ends. We are the trace, the echo, the improbable survivors of a cosmic symmetry, broken before memory. Within the universe's great silence, there remains the question of balance. It is not simply that antimatter disappeared, it is that matter endured. That endurance is not just a condition, but an active principle. Something preserved matter from annihilation. Something protected it, or perhaps allowed it to escape. And so, the notion of baryogenesis enters the stage, not merely as theory, but as a profound speculation on the processes that could have birthed asymmetry itself. Baryogenesis is the name we give to the unknown engine that tilted the scales. In the early universe, when energy densities were incomprehensibly high, the laws of physics did not distinguish between forces as they do now. Electromagnetism and the weak force were unified. The strong force behaved differently than it does today. At such energies, particles were not stable identities but possibilities, fields vibrating with potential. Out of this primordial stew, the very idea of baryon number, the quantity that separates matter from antimatter, emerged. And somewhere in that transition, in that forging of order from plasma, the symmetry cracked. To understand baryogenesis is to plunge into the depths of time, to a moment so brief and dense that our current understanding begins to unravel. It requires that three fundamental conditions, known as the Sakharov conditions, must be met: baryon number violation, C and CP violation, and departure from thermal equilibrium. Each of these is monumental. Each asks the universe to behave, however briefly, in ways that violate its own serene symmetries. Baryon number violation means that particles we consider stable, like protons, could, under certain conditions, decay. In our universe today, protons are stable to extraordinary degrees. We have never observed one decay. But in the early universe, it is conceivable that processes existed, or particles participated in reactions, that changed baryons into other states, non-baryons. This violation opens the door for the number of matter particles to change independently of antimatter. C and CP violation are subtler. Charge conjugation, C, swaps particles with their antiparticles. Parity, P, inverts spatial coordinates, like looking in a mirror. The combination CP is supposed to be a symmetry, a law that says physics remains the same under these transformations. But nature disagrees. In certain decays, particles and antiparticles behave differently, their probabilities unequal. The known CP violation is minute, but it is real. It means that the universe has a preference, a bias, however slight. And the final condition, departure from thermal equilibrium, completes the picture. In equilibrium, reactions proceed forward and backward at the same rate, maintaining balance. But the early universe was anything but calm. It was expanding, cooling, fragmenting. It provided a perfect stage for disequilibrium, a stage where processes could freeze in the midst of change, locking in asymmetries before the dance could reverse. Together, these conditions describe a narrative, a kind of cosmic ritual, high-energy events governed by yet undiscovered physics that generate a slight excess of matter over antimatter, an excess that, through billions of years of evolution, becomes galaxies, stars, oceans, breath. Every breath we take is, in a sense, a continuation of baryogenesis. But what mechanisms, what particles, what forces are responsible? This is where speculation becomes necessity. Grand unified theories, GUTS, aim to merge the three fundamental forces of the Standard Model into a single force, acting at unimaginably high energies. In this framework, quarks and leptons, the building blocks of matter, can transform into one another under extreme conditions. Baryon number in such a universe is no longer sacred. It can be violated through the interactions of hypothetical particles like X and Y bosons. These particles, too massive to exist now, may have decayed in the early universe in ways that favored matter slightly more than antimatter, just enough to survive. Alternatively, the concept of leptogenesis suggests a different route. Perhaps, the asymmetry began not in baryons but in leptons, lighter particles like electrons and neutrinos. If heavy right-handed neutrinos once existed, their decays could have violated CP symmetry and created a lepton asymmetry. Through processes known as sphalerons, this imbalance could then be converted into a baryon asymmetry, producing the matter that endures today. This pathway links the puzzle of antimatter with another cosmic mystery, the mass of neutrinos. Neutrinos, those ghostly particles that pass through matter without notice, may hold secrets deeper than their faintness suggests. If they are Majorana particles, if they are their own antiparticles, then lepton number is not conserved. Such a feature would open the door to the kind of reactions leptogenesis relies upon. Neutrino oscillations, the phenomenon where neutrinos change flavor as they travel, already prove that they have mass, defying earlier assumptions. This mass, though tiny, suggests they may be connected to physics far beyond the Standard Model. In this way, every question leads to another, and the web of understanding grows. The disappearance of antimatter is not an isolated mystery, it is a convergence point. It draws together cosmology, particle physics, quantum field theory, thermodynamics. It demands unity where our knowledge remains fragmented. And so, it drives research forward. We build machines to peer into these moments. The Large Hadron Collider, buried deep beneath the Earth, smashes particles together at energies once found only in the early universe. It has already revealed the Higgs boson, confirming the mechanism by which particles gain mass. But it may, also in time, expose new symmetries, new violations, new reasons for why something remained when everything could have vanished. Beyond Earth, experiments in space seek traces of antimatter. The Alpha Magnetic Spectrometer, mounted on the International Space Station, scans cosmic rays for signs of antinuclei, antimatter heavier than a simple positron or antiproton. The discovery of even a single antihelium nucleus would revolutionize physics, hinting at domains of antimatter in the cosmos or at unknown production mechanisms in the early universe. So far, the search continues without a confirmed signal. But silence is not defeat. It is part of the answer. At the same time, underground detectors search for proton decay, for neutrinoless double beta decay, for the faintest echoes of violations that could have shaped the cosmos. The patience required is immense. These experiments wait not minutes, not days, but years, sometimes decades, for a single definitive signal. It is the science of vigilance, of unwavering belief that the universe is knowable, that its riddles are not eternal. And still, the greatest experiment is the universe itself. Every star that shines, every atom that endures, is a data point. The very existence of structure is a clue. And as our models grow more precise, as our simulations echo reality more closely, we draw ever nearer to a coherent account. Perhaps one day, the conditions of baryogenesis will be not just theorized, but demonstrated. Perhaps we will recreate them, observe them, confirm them, and in that moment we will not only understand why matter exists, we will understand how. That understanding will not change the past. Antimatter will remain absent, but it will give new texture to the present. It will illuminate the path from symmetry to story. It will show that the universe is not arbitrary but expressive, that its rules do not merely allow for existence, but shape it with intention. And with this knowledge, we will look again at the night sky, not just with wonder but with recognition. We will see the galaxies not as distant mysteries, but as the triumph of a brief, silent asymmetry. We will see ourselves not as accidents, but as the fulfillment of a process billions of years in the making. And the silence of antimatter will no longer be a void. It will be a message, one that says, something remained. And from that, everything grew. The quietude of the present universe is deceptive. Behind the stillness of the night sky, beyond the serene drift of galaxies, there lies the memory of violence, of fire, of imbalance. We are the offspring of a profound disruption, one that occurred so early, so absolutely, that everything we see today was born from its ashes. Matter survived, antimatter vanished, but in that vanishing the stage was cleared for creation. The story does not end with the victory of matter. Rather, it begins there. For once the fundamental particles had emerged, once the imbalance was etched into the very fabric of the cosmos, the universe still had no structure. There were no atoms, no molecules, no stars. There was only plasma, hot, chaotic, dense. It would take hundreds of thousands of years before the universe cooled enough for protons and electrons to combine, forming hydrogen, the simplest and most abundant element. That epoch is called recombination, and it is what allowed light to travel freely for the first time, birthing the cosmic microwave background. That light still echoes across the sky, stretched by billions of years of expansion. It is a photograph of the infant universe, a canvas speckled with the earliest imprints of density and temperature, and though it is silent, it tells a story. It confirms the scarcity of antimatter. It affirms the dominance of matter. It reveals, in its spectrum and structure, the echo of that ancient imbalance. From that point forward, the universe entered an era of formation. Gravity, ever patient, gathered matter into clouds and clouds into stars. The first stars were massive, hot, short-lived. They lived and died in spectacular supernovae, seeding space with heavier elements. The cycle of death and rebirth continued, giving rise to galaxies, solar systems, and planets. All of it, the complexity, the beauty, the possibility, was born from that original skew in the matter-antimatter ratio. If the imbalance had been less, if for every billion particles of matter there had been 999,999,999 of antimatter, the resulting difference would have been just 1 particle per billion. Yet that tiny remainder is what formed everything. Every star, every drop of water, every cell in our bodies is descended from that whisper-thin margin. The entire cosmos stands atop that vanishing point. And now, as we gaze outward, we do so not just with eyes, but with instruments, with ideas, with theories. We chart the distribution of galaxies, we map dark matter, we model the expansion of space. In doing so, we seek not only to understand what is, but to retrace how it came to be. The absence of antimatter is not merely a curiosity, it is a foundational condition. It is written into the very bones of the universe. And yet, so much remains unknown. Our models of particle physics, the Standard Model, describe the known particles and their interactions with extraordinary accuracy. But it is incomplete. It does not explain the full asymmetry. It does not account for dark matter, for the masses of neutrinos, for the accelerating expansion of the cosmos. These gaps are not failures, they are opportunities. Each mystery is an invitation to go deeper, to ask more daring questions, to build more refined instruments. One such instrument is the concept of symmetry itself. Symmetry has long been a guiding principle in physics. It suggests that laws should remain unchanged under certain transformations, rotations, reflections, translations. The beauty of a theory often lies in its symmetries. Yet the universe shows us that perfect symmetry is rare. It is in the breaking of symmetry that structure arises. Consider the Higgs field, responsible for giving particles their mass. It permeates all of space like an invisible medium. Particles interact with it, and through that interaction they acquire mass. This process involves spontaneous symmetry breaking. The laws are symmetrical, but the outcome is not. The Higgs field chooses a particular value, and in doing so, the symmetry is broken and mass appears. Without this broken symmetry, there would be no atoms, no chemistry, no life. Similarly, the matter-antimatter asymmetry may be the result of another, deeper symmetry breaking. Perhaps there is a grander theory, one that includes both matter and antimatter as equal components, and the universe in its earliest moments selected a particular path. That choice, like the tilt of the Higgs field, would then become the seed of all existence. Such ideas are not mere speculation. They are subject to testing. The next generation of particle accelerators will probe higher energies, seeking the fingerprints of new symmetries, new particles. Space-based observatories will scan for the rare annihilation signals that might hint at antimatter domains. Underground, detectors will continue their vigil, watching for decays that could rewrite the rules. But perhaps the most profound insight comes not from looking outward, but inward. We are made of matter. Our thoughts, our memories, our dreams, these too are configurations of matter. We are, in a literal sense, the universe becoming conscious of its own asymmetry. Through us, the cosmos reflects on its origins, asks why it exists, and marvels at the improbability of the answer. In this light, the disappearance of antimatter is not just a physical phenomenon. It is a narrative, a singular moment in which the stage was set for everything that followed. It reminds us that reality is not guaranteed, that every existence is contingent, that we live not in the universe as it had to be, but in the universe as it became. This perspective is humbling. It reminds us of the fragility of order, of the narrow margin that separates being from non-being. And yet, it is also empowering. For from that narrow margin emerged complexity, consciousness, creativity. From asymmetry arose music, mathematics, poetry. From imbalance came balance, precarious, imperfect, but real. To study antimatter is to study the absence that gives presence its meaning. It is to explore the shadow that defines the light. It is to recognize that every moment, every breath, is a triumph over annihilation. We are not just survivors of a cosmic selection, we are participants in its unfolding. And as we continue to seek answers, we do so not in despair, but in wonder. The universe has revealed much. It will reveal more. With each discovery, we peel back another layer, revealing the deeper order beneath. We see that even in disappearance there is design. Even in imbalance there is intention. And so we continue, searching, questioning, imagining. We turn our eyes to the stars, our instruments to the void, and our minds to the patterns that bind it all together. In the mystery of antimatter, we find not emptiness but the beginning of everything. The universe we inhabit is steeped in elegance, but that elegance is born from conflict. At its earliest moments, nature was not tranquil. It was fierce, unyielding, a maelstrom of collisions and transformations that shaped the very rules under which existence would unfold. Matter and antimatter were forged in equal measure, but through some primordial betrayal of symmetry, antimatter diminished while matter prevailed. And now, billions of years later, we look back not to mourn what was lost, but to understand how what remains came to be. This narrative, this riddle of survival, touches every corner of physical law. It reaches into the quantum realms of uncertainty, and superposition, climbs into the celestial mechanics of galaxies, and dances through the conceptual frameworks we use to describe reality. It forces us to confront our limitations, not just of knowledge, but of imagination. We are compelled, then, to ask not only how the matter-antimatter asymmetry occurred, but whether our current physical theories are even capable of addressing it fully. The Standard Model, for all its triumphs, is a theory of remarkable precision but bounded scope. It does not explain dark matter, it does not include gravity, and most crucially in this context, it cannot generate the degree of CP violation necessary to account for the magnitude of the asymmetry we observe. That shortfall opens a window, a wide, luminous window, onto the realm of new physics. This realm, which lies beyond the Standard Model, is not a fantasy, but a frontier. Supersymmetry, for instance, posits that every known particle has a heavier superpartner, and some of these particles could alter the CP landscape enough to tilt the early universe toward matter. In this framework, CP violation is not a subtle peripheral effect, but a central engine. Another possibility lies in extra dimensions, the notion that there could be more than 3 spatial dimensions, curled up, hidden from direct perception. Sounds fantastical. But string theory and other approaches suggest it is not only possible, but necessary to unify all fundamental forces, including gravity. Within these higher dimensional frameworks, particles and forces may behave in ways that break symmetry more readily, allowing the matter-dominant universe to emerge as a natural outcome rather than an inexplicable fluke. Even the vacuum itself, the supposed emptiness of space, might be implicated. Quantum field theory teaches us that what we perceive as nothing is in fact seething with fluctuations, virtual particles popping in and out of existence. These fluctuations may have helped shape the symmetry-breaking processes that defined our cosmic identity. In this light, the vacuum is not a passive backdrop, but a co-author of creation. And then there is gravity, the least understood of all the fundamental forces. It is gravity that governs the architecture of the universe, the life cycles of stars, the formation of galaxies. Yet it is also the only force not incorporated into the quantum framework. The effort to unify gravity with quantum mechanics has led to decades of exploration: loop quantum gravity, string theory, holographic principles. Each of these efforts carries with it implications for the nature of time, causality, and symmetry. And each could, in its own way, alter our view of antimatter's disappearance. We are beginning to entertain the possibility that our current understanding of time itself may be insufficient. If time had a different structure at the birth of the universe, if causality unfolded differently, or if multiple temporal dimensions briefly existed, then the processes that governed matter-antimatter interactions might have followed rules that no longer apply. These are not idle musings. They are serious theoretical proposals backed by mathematical rigor and pursued by physicists at the edges of knowledge. And still, for all our theoretical constructs, we are anchored in empirical reality. Every idea must eventually be tested. This is why we build increasingly sensitive detectors to search for the neutron's electric dipole moment, a signature of CP violation beyond the Standard Model. This is why we launch probes to detect rare cosmic rays that may carry antimatter nuclei. This is why we conduct experiments with cold antihydrogen, trapping it in magnetic cages, studying its fall, measuring its spectra. These are not abstract pursuits, they are our instruments of discovery. And yet, perhaps the most audacious experiments are those that have yet to be conceived. As technology evolves, we may find entirely new ways to probe the early universe. We may uncover signals buried in the cosmic neutrino background, or discover patterns in gravitational waves that reveal the fingerprints of symmetry-breaking events. We may even develop quantum technologies that allow us to simulate the dynamics of the early universe with unprecedented fidelity. The tools are evolving, and with them, our capacity to uncover the truth. Meanwhile, the implications of the antimatter mystery extend far beyond the boundaries of physics. They reach into philosophy, into metaphysics, into our very sense of what it means to be. If matter had not survived, there would be no observers, no questions, no awareness. The very act of inquiry requires the asymmetry we seek to understand. This creates a tension. Are we the result of a contingent cosmic accident, or does our existence point toward deeper principles that favor complexity, consciousness, and continuation? Some suggest that the universe is one among many, that in a vast multiverse with varying physical constants, only those with a matter-dominant balance produce structures capable of sustaining observers. This is the anthropic principle, and while controversial, it cannot be dismissed outright. It forces us to confront the limits of what we can know from within our singular universe. It challenges the assumption that every feature of reality must have a necessity behind it. Yet even if the multiverse exists, even if countless other cosmoses unfurl beyond our horizon, that does not diminish the urgency of understanding this one. Our universe is a precious datum. Its asymmetry is a singular story. And if we can understand it, not merely model it, but grasp its cause, then we gain something immeasurable, a glimpse into why there is something rather than nothing. This is the central question of existence, and it is wrapped in the enigma of antimatter. Why is there a universe at all? Why didn't matter and antimatter annihilate completely, leaving a barren expanse of radiation and vacuum? The fact that we are here to ask this question is both the consequence and the clue. So we continue the search, not because the answer is easy, but because the question is essential. Not because we expect immediate clarity, but because each insight draws the cosmos into sharper relief. This is the journey of science, not merely to collect facts, but to construct meaning, to find coherence in the chaos, to build a bridge from the silent beginning to the speaking present. In this light, every particle collision, every data stream, every theoretical paper becomes part of a grand human project, a project to understand our origin not only in physical terms, but in existential ones. We are not separate from the universe. We are its extension, its experiment in reflection. Through us, the universe queries itself. Through us, the mystery of antimatter becomes a mirror. And in that mirror, we see the outline of an answer, not yet clear, but taking shape. We see that from imbalance can come order, from disappearance, emergence, from nothing, everything. As we delve ever deeper into the enigma of antimatter, we begin to recognize that the asymmetry it presents is not merely a question of physics, it is a question of identity. The matter that remains, the matter that forms galaxies, planets, and life itself, carries with it the imprint of choice, an ancient cosmic preference. It is as though the universe, in its first moments, cast a die and chose a side that continues to shape every moment since. This choice, embedded in the laws of nature, is one of the most profound examples of symmetry breaking. Symmetry, after all, represents equality and balance. It implies that the universe's laws apply equally to particles and antiparticles. But what we observe is a broken symmetry, one that favors matter, tipping the scales irrevocably. The question is why? What fundamental principle or mechanism dictated this preference? The search for answers has taken physicists to the cutting edge of theory and experiment. One promising avenue lies in the study of CP violation, the subtle asymmetry between particles and their antiparticles that allows matter to dominate. In the 1960s, the discovery of CP violation in the decay of neutral K mesons stunned physicists. It revealed that the universe's fundamental laws are not perfectly symmetrical, that nature's mirror is imperfect. This discovery opened new doors. It suggested that if similar or greater CP violation occurred in the early universe, it could have produced the matter-antimatter imbalance we see today. However, the CP violation observed in known particles is insufficient to explain the vast excess of matter. This shortfall has inspired a quest to uncover new sources of CP violation, possibly involving particles or interactions beyond the standard model. Neutrinos have become central to this quest. These elusive, nearly massless particles come in three flavors and have the peculiar ability to oscillate between these flavors as they travel. If neutrinos and their antiparticles exhibit different oscillation behaviors, a phenomenon known as leptonic CP violation, it could provide the missing piece of the puzzle. Detecting such differences would offer vital clues to the processes that generated the cosmic asymmetry. To explore this, experiments like the Deep Underground Neutrino Experiment, DUNE, are being constructed. These colossal detectors, buried deep beneath the Earth, will observe neutrinos sent from particle accelerators hundreds of miles away. By measuring the subtle differences in neutrino and antineutrino behavior, they hope to capture evidence of CP violation that may have shaped the early universe. Parallel to this, the Large Hadron Collider and other facilities continue to hunt for new particles predicted by theories such as supersymmetry and grand unified theories. These hypothetical particles might have decayed in ways that favored matter, leaving behind the residue of imbalance. Discovering them would not only explain the antimatter mystery, but also revolutionize our understanding of the fundamental forces. Yet, despite decades of research and billions of dollars invested, the antimatter asymmetry remains unresolved. The universe has withheld its secret, challenging us to refine our theories, enhance our instruments, and broaden our perspectives. This mystery embodies the very essence of scientific pursuit, the relentless drive to understand the unknown. Beyond physics, the matter-antimatter asymmetry touches on philosophical realms. It challenges notions of inevitability and chance. Was the dominance of matter a cosmic accident, a random fluctuation frozen into reality? Or does it reflect deeper principles, perhaps inherent biases woven into the fabric of existence? These questions inspire reflections on purpose, on the nature of reality, and on humanity's place within it. In the grand tapestry of the cosmos, antimatter's disappearance is a silent verse, a missing harmony that shapes the melody of existence. It reminds us that the universe is not static, but dynamic, not perfectly balanced, but beautifully imperfect. It invites us to embrace complexity and uncertainty as integral to creation. As our journey continues, fueled by curiosity and guided by reason, we edge closer to unraveling the mystery. Each experiment, each observation, each theoretical breakthrough builds a bridge from ignorance to understanding. And in doing so, we deepen our connection to the cosmos. Ultimately, the story of antimatter is the story of us, of matter that survived, of consciousness that emerged, of questions that inspire. It is a testament to the resilience of existence and the wonder of discovery. In seeking to understand why the universe exists, we come to understand ourselves. The tale of antimatter's vanishing is more than a chapter in cosmic history. It is the cornerstone upon which the universe's narrative is constructed. Without this fundamental asymmetry, the cosmos would be a vast expanse of pure energy, a featureless sea of photons left over from mutual annihilation. There would be no stars to illuminate the darkness, no planets to harbor life, no beings to ponder their existence. This profound consequence urges us to reflect on the nature of reality itself. The laws of physics, so elegantly formulated, reveal a universe that favors imbalance. In this imbalance lies the potential for complexity, for differentiation, for emergence. The symmetry that might have annihilated everything instead broke, giving rise to structure and order. Exploring the early universe demands a multidisciplinary approach, blending cosmology, particle physics, astrophysics, and quantum theory. Modern cosmology paints the Big Bang not as a singular event, but as a rapid expansion phase known as inflation. During inflation, tiny quantum fluctuations were magnified to cosmic scales, seeding the density variations that would later collapse into galaxies and stars. These fluctuations might also have influenced the matter-antimatter asymmetry. The mechanisms that triggered inflation could have created conditions ripe for symmetry breaking, conditions that favored matter's survival over antimatter's. By studying the cosmic microwave background radiation, we can detect the imprints of these primordial fluctuations, offering a window into processes that shape the universe's fundamental properties. Moreover, the interplay between particle physics and cosmology has revealed fascinating possibilities. Models such as baryogenesis propose scenarios where interactions beyond the standard model generated the observed asymmetry. For instance, electroweak baryogenesis suggests that during the electroweak phase transition, certain processes could have produced more baryons, matter particles, than antibaryons, tipping the cosmic balance. Alternatively, leptogenesis posits that an asymmetry in leptons, particularly neutrinos, could have cascaded into a baryon asymmetry through processes that violate lepton number conservation. This chain reaction elegantly links the properties of elusive neutrinos with the very existence of matter in the universe. Testing these theories requires extraordinary experimental sensitivity. Particle accelerators recreate conditions similar to those fractions of a second after the Big Bang, while neutrino observatories and cosmic ray detectors search for rare signals that could confirm the predicted asymmetries. Each discovery or null result narrows the field of possibilities, guiding us closer to the truth. The question of antimatter also raises technological and practical considerations. Understanding antimatter better opens potential avenues for energy production, medical applications such as positron emission tomography, PT, and even propulsion systems for future space travel. While antimatter remains challenging and costly to produce and store, it embodies a potent source of energy, a mirror to matter's power. Beyond practicalities, antimatter captivates the imagination. It invites us to contemplate parallel realities, mirror worlds where everything is reversed. Some speculative theories suggest regions of the universe dominated by antimatter might exist beyond our observable horizon, separated from us by boundaries where annihilation would occur. Detecting such domains would revolutionize cosmology, reshaping our understanding of the universe's global structure. However, current observations indicate our observable universe is overwhelmingly matter-dominated. This uniformity supports the idea that the asymmetry was established before the universe became transparent, during epochs inaccessible to direct observation but inferable through relic radiation and particle abundances. The mystery of antimatter is thus a beacon, calling scientists to explore ever deeper. It challenges us to develop new theories, build more precise instruments, and expand our conceptual horizons. It reminds us that the universe is a dynamic interplay of symmetry and asymmetry, of order and chaos, of creation and destruction. As humanity advances technologically and intellectually, our capacity to probe the early universe will grow. Future telescopes, detectors, and colliders will push the boundaries of knowledge, revealing phenomena currently beyond our grasp. Perhaps one day, we will uncover the definitive mechanism that skewed the balance in favor of matter, illuminating the dawn of existence itself. In embracing this mystery, we also embrace our place in the cosmos, not as passive observers but as active participants in the unfolding story of reality. The asymmetry that allowed matter to survive also allowed us to exist, to question, and to dream. It is a reminder that even in the vastness of space and time, small imbalances can lead to profound consequences. And so, the mystery of antimatter continues to inspire not only scientific inquiry but also a profound sense of wonder. It is a testament to the universe's complexity and to the human spirit's unyielding quest to understand. Through this quest, we glimpse the intimate connection between the cosmos and ourselves, a connection forged in the subtle imbalance of particles that shaped everything we know. The mystery of antimatter's near disappearance compels us to look not only outward but inward, into the nature of the fundamental forces that govern reality. Among these forces, the weak interaction stands out as uniquely capable of violating certain symmetries, making it central to the matter-antimatter puzzle. Unlike the electromagnetic and strong forces, which treat matter and antimatter nearly identically, the weak force introduces subtle differences, permitting processes that can distinguish between the two. This property of the weak interaction is the cornerstone of CP violation. When combined with charge conjugation, C symmetry, which swaps particles with their antiparticles, and parity, P symmetry, which inverts spatial coordinates, the combined CP symmetry was long believed to hold universally. Yet experiments in the 20th century shattered this belief, revealing that certain weak decays violate CP symmetry. This breakthrough exposed a crack in nature's mirror. The significance of CP violation cannot be overstated. It provides a mechanism by which the early universe could have produced more matter than antimatter. However, the CP violation observed so far is insufficient to explain the current cosmic matter dominance. This insufficiency suggests that other sources of CP violation exist, potentially hidden in particles or interactions yet to be discovered. Extending our understanding requires exploring beyond the standard model of particle physics. Grand unified theories, GUTS, seek to unify the electromagnetic, weak, and strong forces into a single framework, predicting new interactions and particles. These theories often predict enhanced CP violation and mechanisms for baryogenesis, the generation of baryon asymmetry. Moreover, supersymmetry, SUSY, a proposed extension of the standard model, introduces a host of new particles, each a partner to known particles, but differing in spin. SUSY models can provide additional CP violation sources, potentially explaining the matter-antimatter imbalance. Although SUSY particles have not yet been observed, ongoing experiments continue to probe their existence. Another fertile ground for investigation is the realm of neutrinos. The discovery that neutrinos have mass and oscillate between flavors opened new avenues for exploring CP violation in the lepton sector. If neutrinos violate CP symmetry differently than antineutrinos, this could have led to leptogenesis, an asymmetry in leptons that eventually translates into baryon asymmetry through processes that convert lepton number to baryon number. Large-scale neutrino experiments, such as the Deep Underground Neutrino Experiment, DUNE, and hyperchemiocande, are designed to detect and measure CP violation in neutrinos with unprecedented precision. These projects involve sending intense neutrino beams across vast distances to observe oscillation patterns and compare neutrino and antineutrino behaviors. Their results may hold the key to understanding the universe's matter dominance. In parallel, precision measurements of the neutron's electric dipole moment, EDM, are underway. A non-zero EDM would signal CP violation beyond what is known, offering another pathway to unravel the antimatter mystery. Experimental advancements are pushing the sensitivity of EDM measurements to extraordinary levels, narrowing the window where new physics may reveal itself. Beyond experimental pursuits, theoretical developments continue to shape our understanding. Advances in quantum field theory, string theory, and cosmology propose novel mechanisms and scenarios that could produce the necessary asymmetry. Concepts such as spontaneous CP violation, where symmetry is broken dynamically rather than explicitly, offer intriguing possibilities. Additionally, the study of cosmic inflation, an exponential expansion phase in the universe's infancy, may shed light on how initial conditions favored matter. Inflation could amplify tiny asymmetries, embedding them into the large-scale structure of the cosmos. The interplay between inflationary dynamics and baryogenesis remains an active research area. Yet, despite the strides made, the question remains profoundly challenging. The origin of the matter-antimatter asymmetry is a puzzle at the intersection of the very large and the very small, bridging cosmic evolution and subatomic phenomena. It calls for a synthesis of disciplines and a unification of physical laws. The pursuit itself enriches science and humanity. It pushes technology, inspires innovation, and fosters international collaboration. It reminds us that understanding the universe is a collective endeavor, transcending borders and cultures. At its heart, the antimatter mystery is a testament to nature's complexity and subtlety. It reveals a cosmos that is not simply symmetrical and static, but dynamic and asymmetric, allowing for diversity and life. It is a mystery that challenges us, invites us, and ultimately connects us to the profound narrative of existence. In contemplating the antimatter enigma, we encounter not only questions of physics, but profound reflections on the nature of existence itself. The imbalance between matter and antimatter is a reminder that the universe is not governed by perfect symmetry, but by delicate imperfections that give rise to complexity and life. These imperfections are woven into the fabric of reality, shaping the cosmos from the very beginning. This narrative forces us to reconsider our place in the grand scheme. We are not mere observers of the universe, but active participants in its unfolding story. Our very existence depends on a subtle asymmetry that emerged in the first fractions of a second after the Big Bang. Without this asymmetry, the universe would be a featureless expanse of energy, devoid of the atoms that compose stars, planets, and living beings. Such reflections inspire a sense of wonder and humility. They remind us that the universe is a dynamic and evolving entity, filled with mysteries yet to be unraveled. The antimatter puzzle beckons us toward deeper understanding, urging us to look beyond the surface and explore the fundamental principles that govern reality. Moreover, the story of antimatter challenges us to embrace uncertainty and complexity. It teaches that not all answers are straightforward or complete, that progress often comes through the interplay of theory and experiment, of bold hypotheses and rigorous testing. This iterative process lies at the heart of scientific inquiry and human curiosity. As technology advances, so too does our ability to probe the early universe. New generations of particle accelerators, neutrino observatories, and cosmic detectors will push the boundaries of knowledge. Each discovery will bring us closer to unraveling the origins of matter's dominance, illuminating the processes that shaped our cosmos. Yet, even as we approach these answers, the mystery of antimatter reminds us that science is an ongoing journey. Every solution uncovers new questions. Every revelation opens new frontiers. It is this endless pursuit that defines us, that connects us across generations and civilizations. In this journey, we find a profound unity between the cosmos and ourselves. The atoms in our bodies were forged in stars, themselves composed of matter shaped by the early universe's asymmetry. We are, quite literally, made of matter that survived the cosmic annihilation, carrying within us the legacy of that primordial imbalance. Thus, the mystery of antimatter is not just a scientific question, but a human one. It speaks to our origins, our nature, and our destiny. It challenges us to understand where we come from and what it means to exist. In seeking these answers, we engage in a dialogue with the universe, a dialogue that is as old as time itself. As we continue this exploration, we embrace the unknown with courage and curiosity. We stand at the threshold of discovery, ready to unveil the secrets that antimatter holds. This quest is a celebration of human intellect and spirit, a testament to our enduring desire to comprehend the cosmos and our place within it. As we draw closer to the heart of the antimatter mystery, we are compelled to recognize the profound implications that its resolution may hold, not only for physics, but for the broader tapestry of knowledge and philosophy. The asymmetry between matter and antimatter is a fundamental clue to the very origin of the universe's structure, and understanding it could unlock new principles that transcend current scientific paradigms. One particularly exciting frontier lies in the interplay between quantum mechanics and gravity, two pillars of modern physics that remain stubbornly disconnected. The early universe, a hotbed of extreme energies and densities, was a realm where these forces intertwined. It is possible that the origins of the matter-antimatter imbalance lie within a theory of quantum gravity, a framework yet to be fully realized. Quantum gravity theories, including string theory and loop quantum gravity, aim to unify the forces of nature, potentially providing novel mechanisms for symmetry breaking. Within such frameworks, The very nature of space-time, particles, and forces may emerge from more fundamental entities or principles. If antimatter asymmetry emerges naturally from these deeper layers of reality, it would revolutionize our understanding of existence. Moreover, the mystery of antimatter raises questions about the multiverse, the hypothesis that our universe is one of many, each with its own laws and properties. In this grander picture, matter-antimatter asymmetry might be a feature specific to our cosmos, one realization among countless others. Such a perspective challenges our notions of uniqueness and encourages us to contemplate the broader landscape of possible realities. While these ideas remain speculative, they inspire a spirit of adventurous inquiry. The history of science teaches us that even the most radical concepts can gain empirical support over time, reshaping our worldview in unexpected ways. The antimatter puzzle serves as a catalyst for this intellectual boldness, pushing us to imagine beyond the known. In practical terms, future advancements in observational cosmology, particle physics, and astrophysics will be essential. Upcoming. Telescopes will peer deeper into the cosmic microwave background, searching for subtle imprints left by primordial processes. Particle colliders and neutrino detectors will continue to push the frontier of precision measurements, seeking traces of new physics. Additionally, the development of quantum technologies, quantum computers, sensors, and communication systems may provide new tools to simulate and analyze the complex interactions that led to the matter-antimatter imbalance. These technologies promise to open windows into phenomena previously too intricate to model accurately. The journey to solve the antimatter mystery is emblematic of the human quest for knowledge. It exemplifies how curiosity, combined with rigorous inquiry and technological innovation, can unlock nature's deepest secrets. This quest transcends individual disciplines, uniting physicists, cosmologists, engineers, and philosophers in a common pursuit. Ultimately, the asymmetry that gave rise to the universe we inhabit is more than a scientific problem. It is a profound narrative about origins, existence, and the nature of reality. Each step toward understanding brings us closer to comprehending why the universe exists at all, why it is made of matter, and how complexity and life emerged from the primordial chaos. In embracing this mystery, we embrace the spirit of discovery itself, a spirit that defines us as a species and connects us to the cosmos. The universe's preference for matter over antimatter is a silent but eloquent testament to the delicate balance that sustains all that we know and cherish. As we reach the culmination of our exploration into the mystery of antimatter, it is fitting to reflect on the profound journey we have undertaken, one that spans the earliest moments of the cosmos to the cutting edge of modern science. The question of why the universe exists, why matter prevails over antimatter, is not merely academic. It is the foundation upon which the entire cosmic narrative is built. From the searing furnace of the Big Bang, where matter and antimatter emerged in nearly equal amounts, to the subtle processes that tipped the balance in favor of matter, we see a universe shaped by asymmetry. This imbalance is the source of all structure, all complexity, and ultimately all life. Without it, the stars would not shine, the planets would not form, and consciousness would never arise. The pursuit to understand this asymmetry has driven humanity to the forefront of scientific inquiry, forging new technologies and inspiring innovative theories. It has revealed the limitations of our current knowledge and illuminated pathways toward deeper understanding, pathways that may one day unify the fundamental forces and reveal the ultimate nature of reality. Yet, beyond the equations and experiments, lies a narrative rich with philosophical significance. The matter-antimatter asymmetry invites us to consider the nature of existence itself, the delicate interplay between symmetry and asymmetry, order and chaos, chance and necessity. It challenges us to recognize the beauty inherent in imperfection and the creativity born of imbalance. This cosmic mystery also connects us intimately to the universe, We are made of matter that survived the annihilation of antimatter. We carry within us the legacy of that primordial choice. Our existence is a testament to the subtle laws of physics that shaped the cosmos billions of years ago. As science progresses, we remain poised on the edge of discovery. New generations of experiments and observations will continue to peel back the layers of this mystery, offering glimpses of the profound processes that gave birth to the universe as we know it. Each discovery will deepen our understanding and perhaps reveal new questions, continuing the eternal cycle of inquiry. In the end, the mystery of antimatter is a celebration of the universe's complexity and the human spirit's relentless pursuit of knowledge. It is a story of survival and transformation, of the subtle forces that shape reality, and of our place within this vast cosmic tapestry. The universe exists because matter won the silent, invisible battle against antimatter. This truth connects every atom in our bodies to the earliest moments of time and space, reminding us that we are, in the grandest sense, children of the cosmos, born from a delicate asymmetry that made all existence possible. The journey to understand why the universe exists through the lens of antimatter is far from over. It is a journey that will inspire generations to come, a testament to human curiosity, ingenuity, and wonder. As we look to the stars and beyond, we carry with us the hope and determination to one day fully unravel this profound mystery. And in that pursuit, we celebrate not only the universe, but the extraordinary capacity of the human mind to seek, to question, and to understand.